Hey, what's up, chemistry people? It's Mr. Boylan. Hope you're ready for some more chemistry fun. Our content objective for today: I can identify production of heat or light, formation of a gas, formation of a precipitate, and/or a color change as possible evidences that a chemical change has occurred, and then describe this change in various equation formats. Gonna be a good time. All right, so let's break it down a little bit. You're gonna have to be able to classify changes either physical or chemical, or ambiguous, and you're gonna have to do so based on observations that are both macroscopic in nature and those that we cannot see based on the rearrangement of the covalent and non-covalent interactions. What's going on? Are we breaking those bonds to form new things, or are we just breaking intermolecular forces and the identity of the material stays the same? And then secondly, you're going to have to go back and forth between sort of describing these macroscopic observations of change to chemical equations. So what are you observing big picture, and how can you describe that in a chemical equation? And also, how can you describe it in a sort of particle view? And then lastly, you're going to apply the concept of conservation of atoms, conservation of mass, what a great law, to the rearrangement of atoms in various chemical processes. All right, so first things first, a couple of definitions. Physical changes involve only the making and breaking of intermolecular forces between substances. No new substances are formed. So take a quick look at this sample of water. As we melt water, it's an example of a physical change. The only thing that is being broken here are the intermolecular forces, in this case, the hydrogen bonds that exist between the water molecules, but we're not breaking the bonds that exist between the oxygen and hydrogen atoms. Chemical changes, on the other hand, involve the making and breaking of intra-bonds, or your ionic and covalent bonds. They're the ones between substances, and we form new things in a chemical change. So here's a representation of a chemical change. Note that we're breaking the bonds that are within the molecules, reforming new bonds to create completely new products. Okay, so sometimes just using your eyeball, it can be a little difficult to distinguish between chemical and physical changes. So we have to consider what's going on with the bonds and what types of bonds are being broken, what types of forces are being broken, to help us identify whether or not it's chemical or physical. Some things that you can look for at the macroscopic level to help you let you know you've got a chemical change versus a physical change. 1, if you see color change. 2, if you see a solid form, aka a precipitate. Or 3, if you observe an energy change. Oftentimes we'll see that in the form of light or heat. Okay, and then once we observe these changes at the macroscopic level, we have to then describe them in a way that we can relate it to other chemists, other scientists, and people at large. So a couple of things first. It's really important when you observe chemical and physical changes that atoms and mass are conserved. They're neither created nor destroyed in any chemical or physical process. 2, it's important that you recognize that a chemical equation is just a symbolic representation that reflects that conservation of atoms or mass by being balanced. So it's important to note that as you look at the following example of a balanced chemical equation, that all of the atoms are in equal numbers on either side of the equation. So here are 3 examples of balanced chemical equations that we use to represent macroscopic changes. Again, note that the number of atoms, carbon, hydrogen, and oxygen, are in the same numbers on either side of the chemical equation. And that's super important as we move throughout the year. Before you begin to do anything with these chemical equations, you've got to make sure they're balanced to reflect the law of conservation of mass. Number 3, you can also represent those macroscopic changes using what are called particulate or particle representations. But again, you're going to have to show equal numbers of particles before and after the reaction. Here's a quick example of what we're talking about in particulate representation, where you just sort of help us better visualize what's going on with the atoms in the chemical reaction. Sort of an application here: if you know the mass of the reactant, because the atoms and therefore mass is conserved, you can also figure out what the product masses are, or vice versa. If you know the product masses, you can figure out the reactant masses. Law of conservation of mass, it's a good one. And so ultimately, just driving this point home here, the conservation of atoms in mass means that as atoms travel throughout the universe from one situation to another, they are never created or destroyed. Rather, they are simply rearranged to form different compounds. Okay, and then the last part of your notes here, we're going to look at making sure we know how to balance chemical equations to show that conservation of mass. It's really important that you recognize, as we'll learn in Okay, it's really important that you recognize here that the relationships of the coefficients between your reactants and products in a balanced chemical equation is called stoichiometry, and we'll get to that in just a couple of days. But some rules to keep in mind when we are balancing chemical equations. One, the same number and type of atoms must be present in the reactants and the products. Two, coefficients are placed in front of the chemical formula. It's really important that you not try and change the subscripts in correct chemical formulas. If you change the subscripts, you create a completely different compound and no longer reflects what you observed at the macroscopic level. Okay, and number three, sometimes, for the most part last year, but not always as we'll find this year, it's necessary to have all coefficients expressed as the lowest possible integers. And again, we'll talk about some of the exceptions as we come across them, but for the most part, we're going to try and go for lowest possible integer. Okay, and as you walk through the process of balancing chemical equations, it's not really a scientific process, even though it is really important to do. It's really just trial and error, but there are a few things you can keep in mind to help the process move a little bit more smoothly. One, balance your metals first, then balance your nonmetals. Save hydrogen and oxygen for last. You should always balance polyatomic ions as units. It makes it a little bit easier there, as long as they appear on both sides of the equation. And then be sure to balance charges, and we'll talk a lot more about that when we get to redox reactions here in just a couple days. And then lastly, just breaking down the anatomy of a chemical equation. Don't forget, you got your reactants, what is it you start with, your products, what you end up with. The coefficients there will represent your number of molecules, and then your subscripts represent the number of atoms within that molecule. Or if we're looking bigger picture, they could also represent number of moles.